Hello all, let's get started. We'll be talking about chapter 11, which is about walls, and the governing code is ACI 318-14. Again, structural codes like this, like the ACI, are often heavy on text but light on visuals. My goal is to take these dense, complex clauses and bridge the gap with some simple chicken scratches that I draw on the code canvas. By layering these chicken scratches directly onto the code canvas, we transform abstract rules into clear mental images. This visual association will make it much easier for you to recall specific requirements when you are under pressure in an exam. This is mainly that I'm not going to cover every little detail, but we'll be talking about. We'll keep the PE breadth or SE breadth level rigor, and we'll be talking about only those topics, right? So let's get started. As you see, chapter 11 here is about the walls. We're talking about ACI 318 2014 version, right? So chapter 11 starts from page number 165. So that's from here. Let's start. So that's about walls, right? Mainly three different types of walls: cast in place, precast, and precast on site, including tilt up. So the chapter is about these three different walls, right? And there are some special structural walls. We'll not be talking about those, but then those are covered in chapter 18. We'll cover that in a later video, maybe. If your plain the wall is plain concrete, no reinforcement, then it's according design should be according to chapter 14, right? Again, if it is cantilever wall and all that, retaining wall, then you'll have to design it according to 22.2, right? About some materials, concrete, properties should be according to chapter 19. If the reinforcement related information is available, chapter 20. Wall is made of both concrete and reinforcement. We are talking about reinforced walls. Material design, detail requirement, embedments and all that, chapter 20. Connection to the other members, again, chapter, this particular section here. But in today's intent is to talk about the different forces and how do you calculate different strengths of the wall. So we will not be covering these things in detail, right? So let's move on. Let's start with let's start with this one here. So if you have a wall or something like that, right? Then what is the minimum thickness requirement? So that depends upon if you're, again, we have a table. My favorite thing, my standard thing is you will have to figure out if you fall here, and then you will have to think about in this direction, right? So if you are bearing wall, meaning walls that have a significant component, are designed for axial loads and have a significant component of axial load. When I say axial load, let's say here is the wall, this is the height of the wall, let's call it HW, then I'm talking about axial. Maybe it is supporting, the wall is supporting a concrete slab or something like that, right? So if it is a bearing wall, then the greater maximum of these two things, one is 4 inch, the other one has to do with a fraction of the unsupported length, right? So now you have a wall, then maybe the wall is maybe supported here on the top, and maybe it is supported here on the bottom. This support is like a support that restrains the rotation, whereas this support is just a lateral support. So anyway, you take the unsupported length, take a fraction of it, 1/25th of the unsupported length, and then you also take 4 inches, find the maximum value. That's how you decide the minimum thickness of the wall. Now for a non-bearing wall, you get here. Again, you do two things. non thickness is not as critical for a non-bearing wall as a load-bearing wall, because this fellow is taking the load of something, and you need to. So there are stringent guidelines on thickness of a bearing wall, whereas on this one, little bit relaxed, 1/30th of the unsupported length, and 4 inches. Find the greater of two. That's how you decide, right? So if if you fit here, then exterior basement and foundation walls, then your minimum is minimum thickness. This is not the final thickness, obviously. Minimum thickness is 7.5 inches there, right? So that's about the thickness table. Let's keep going. We'll have to cover a lot of ground here. So the general strength related. Now we are slowly getting into the strength. Idea of this chapter is to see how we can find out the axial strength, the in plane moment strength, out of plane moment strength, and things like that. Right. So strength shall be calculated in accordance with factored load combinations. Right. For example, you have dead load and live load. So you do 1.2 dead load plus 1.6 times of live load and a bunch of other factors in chapter 5. That's what they're referring to here. And required strength shall be calculated in accordance with all these analysis procedures, which are in chapter 6, right? Because this is a wall, so obviously slenderness effect is going to change the results. So you'll have to go through these sections to figure out how you can incorporate the effect of slenderness into your wall design. Right? There is also a special alternate procedure for out of plane. Now we'll talk about what out of plane, what in plane, and all that is. And it is section 11.8. We'll be looking into those details as well. I like to stop at pictures. This is a very nice picture here. Very clear presentation. For example, this is the wall. That is the HW, and you see this width being called as LW, length of wall, and this is the thickness of the wall, which will be usually called H, small h, right? So if that is a wall, then you have your in-plane shear, meaning when they say plane, they're referring to the plane of the wall. So that plane itself, any shear within that plane is called in-plane shear. So that is this fellow here. Axial force, obviously, axial along the height of the wall. So that is the axial force there. You can have a moment in the plane, which is, let's say this is the plane. You can have a moment about that. So that is your in-plane moment. And you can have a moment that is trying to uh, bend about the weak axis, and that is the out-of-plane moment, right? So in-plane shear, axial force, in-plane moment, out-of-plane moment. And out of plane shear. Out of plane shear is you have this particular wall here like that, and then maybe a lateral force is trying to um, shear the wall, and then that means this is the area that is going to come into play. Right. So we talked about that jugglery here. Let's move on to the next one. So this is about the wall shall be designed for eccentric axial loads, meaning let's say you have a wall like that, right? Let's say we are looking at this wall from this direction. That means you just see a simple rectangle like that. The load can be, so let's say this is the center line of the wall. The load can be exactly here, or it can be slightly eccentric. So that from the center line, that is called the eccentricity, and maybe you have an axial load. So you cannot ignore the eccentricity. You need to design for eccentricity. You need to account for the eccentricity is what this is saying here, right? Um, Factored axial force and moments. Wall shall be designed for maximum factored moment mu, and this will come from our load cases, our load combinations, and factored axial force pu. Again, this will come from different load combinations. So obviously we need to design for that. But the factored axial force at a given eccentricity should not exceed the capacity, right? So P n max this is like the nominal capacity, and then you multiply it with the strength reduction factor. So your PU shall be less than the applied load, should be less than or equal to PN max. PN max is again given here in this section. So this is the, if you have designed a column, then you know, you would have seen that section. Pretty common when it comes to calculating the axial load capacity. For example, you have a column, then your PN will be, so this PN max here, PN max is, for example, if you have a column, that column has all the ties, then the code says use 0.8 times of P0, and then the P0 is nothing but um, it's something like this, equation like this. You can find these equations in 22.4.2.1. So it is a function of 0.8 empirical constant, FC dash times of AG, a gross area minus area of steel, plus um, the yield strength times of AST, right? So this is a contribution from steel. This part is contribution from concrete. You find P naught, and if your column has, let's say this is your column, and the column has a bunch of ties in it, ties everywhere, right? You have a tie, and there's a longitudinal bars. Then you'll have to do this. So that 0.8 factor will become 0.85 if it is if it is a circular column with those spirals and all that, right? So anyway, so that's a side thing here, but then um, the main point is the P naught max should be computed from that particular section here. And reduction factors, again, you know the reduction factor, strength reduction factor. It's a simple, you'll pick it up from, I think, table 21.2, 21.2.2. It's a simple graph between the strain in the steel versus the strength reduction factor, right? So you decide the strength reduction factor that needs to be used in this term based on um, what the strain in your steel is, right? So it's a curve that looks like this. I'm sure you would have seen all this. It has three different zones mainly. Like I said, this is the strain in steel. There are three different zones. This is when, for example, if you are using 60 KSI steel, then the strain the T value is 0.002. So if you are below this particular strain, in this area is called the compression controlled area, right? Whereas if you are above a certain strain in steel, if your strain in steel um, is let's say 0.005 per the code, these are not made up numbers, they are per the code. So there is a decent strain still. That means you are in this region here, which is the tension control area, right? So if you are in tension control area, if your strain is here, tension control area, then you will pick up the phi value from here, which is usually 0.9, 0.9, right? And if in the compression control area, usually it is 0.65. Whereas if you have spiral reinforcement, then it is I mean, the curve is all there in the code, but then if you have spiral reinforcement, then it is 0.75, something like that, right? Anyway, the main point is the phi value is not a standard fixed value. It depends upon the strain in steel. If your strain in steel falls within the tension controlled area, you pick up your phi value accordingly. If the strain in steel falls in the compression controlled area, then you pick up the value 0.65 accordingly. If it is in the transition area, you obviously, let's say it is here, then you have to interpolate between this value, point A and point B, right? Uh, so that's about it. Again, this is available in table 21.2.1, that particular table there. Okay, let's keep going. That's a slightly side topic there. I'm sure you are familiar with, now we are slowly getting into design strengths. I'm sure you are familiar with this. In a phi times of a Pn, This is the nominal strength. You're reducing the nominal strength, and then that should be greater than or equal to the load coming from. This is the demand load coming from your different load combination. That's a common pattern. I mean, I like to catch those patterns. The same thing here. Mn, phi times of Mn greater than or equal to Mu. This is from the loads, applied loads, whereas this is the strength of the section. You reduce it based on uh, reduce it through a strength reduction factor, right? So the reduced strength should be greater than the uh, loads, ultimate loads, or the demand, right? Same thing for shear. P is for axial, M is for the moment, and V, as you know, is for the shear. Excuse me if I'm repeating all the fundamentals, but then idea is to correlate the I mean, if you see something like phi Pn, you must be immediately you must be in a position to associate with the axial force, and not Pn is the nominal capacity, phi is the strength reduction factor, and all that, right? So the story here is the same like any other section. We'll have to satisfy this to as we design. Now, axial loads in plane and out of plane flexure, right? So that means you have the wall like that. We are talking about wall like that. We are talking about a wall being axially loaded, and maybe the wall um, is subjected to a out of plane moment. Maybe the wall of the wall is subjected to in plane moment, right? So if the moment is within this plane, then it is in plane. If the moment is about this axis, then it is out of plane, right? So for bearing walls, again, the pattern here is they talk about bearing walls, and they also talk about non-bearing walls. So depending upon where you fall, which wall you are designing, you'll have to read this or you'll have to read that, right? So for bearing walls, Pn and Mn shall be calculated in accordance with that particular chapter here, right? Um, Mn can be in plane, Mn can also be out of plane, right? But there is an alternate procedure, um, which is according to 15.11.5.3. For the alternate procedure to hold good, there are some assumptions which are highlighted here. So this is called the simplified design method, and it is for axial plus out of plane flexure. When again out of plane flexure, you have a wall like that. In plane is within the wall. Out of plane is about that axis. Let's say that axis, you have a moment about that axis, which is going to try to buckle the ball, right? Like that, right? So axial load, out of plane flexure. There is a simplified procedure, correct? Um, and this is for let's back up a second here. Simplified procedure for bearing walls, right? So so your wall is a bearing wall, and you have axial and moment. Um, if you satisfy certain conditions, we'll talk about those conditions, then you can use a simplified procedure to calculate your capacity. Idea is to always to find out by the end of this chapter, we need to understand how to find out the capacity of a wall, axial capacity, how to find the bending capacity of a wall, how what is the minimum thickness, what is the minimum percentage of longitudinal steel, what is the minimum percentage of transfer steel, things like that, and some cover and some uh, basic stuff, right? So again, simplified procedure is applicable if the resultant force is within middle third of the section. Meaning, I don't want to read the entire thing, but then let's say you have a wall like that, correct? Looking at the wall in this direction, let's say you have the wall section there. Here is the center line. You can divide this width h into three h by 3, h by 3, and h by 3, right? That means, so let's say I have my So let's say this is the middle h by 3, correct? So if your resultant of p and the moment falls within that region, only then a simplified approach can be used, right? So the simplified, if you see in this equation, there is no m value here. That means the moment is, the effect of moment is being considered in terms of an slenderness factor, right? But then for this method to apply, the resultant of your P and M should lie within the middle third width of the column, right? So that means, let's say you have a P and let's say you have an M, you can replace that um, with the P acting exactly at the center, P, and another P. Sorry, you can replace that with let's do this again. So you have a wall like that. Let's say you have a P and then M. This is your axial load. This is your moment. You can replace that, as you have seen numerous times. You can replace that with a P acting eccentrically. This is a new P. Let's call it P dash, and that acting at an eccentricity E, right? So so that E value that you calculate, that E is nothing but your M by P, because P times E is equal to M. So that E eccentricity should lie within, from H by, in the middle third. That means from the center line, this value here is like H by 6. If this is H, right? Thickness of the wall. And it can, the eccentricity, the P can also be also fall on this side. If you have a M going the other way, if you have a M going the other direction, then your P will be somewhere here. The fictitious P dash will be somewhere here. And that if that P, the fictitious P, based on this calculation, falls within this portion or this portion, only then this particular simplified procedure can be applied, right? So indirectly, the effect of M is not significant, and it is not causing tension in the wall, right? So assuming you satisfy that condition here, again you can read all this, but then that is in short. In short, it is about your eccentricity landing in the middle third of the column. When they say middle third, it is h by, so this from here to here is um, h by 3, but then from here to here is h by 3 by 2, which is h by 6. So that is the h by 6 that is being referred to. So if you do that, then your axial nominal strength, Pn, n is the nominal, that's the strength of the wall. The nominal strength can be calculated using this formula. Here, you know what, this is an empirical constant. You know Fc prime is the compressive strength of concrete, gross area of the column being considered, wall being considered, meaning, let's say you are only considering, let's say this is the wall, then this is the gross area that we are talking about, right? Or maybe you're only considering 1 foot section of the wall, then this is the area that is being talked about, right? So you have thickness and you have the 12-inch length, right? So we covered that. We know what FC dash is. We know what AG is. KL, this is something like KL by R, right? KL by R whole square. So this is like the slenderness ratio. K is the factor that depends upon the boundary condition. Meaning, if you have a wall, and there's a table below, I'll show you where if you have a wall like this and like that, meaning here is the wall, but then it is not allowed to, it is restrained, lateral motion is restrained, the rotation is not restrained. Here the rotation is restrained. So there is a certain, this is how it's gonna deform. So there is a certain K value for this, which we'll talk about. I'll show you in the table below. If you have pin wall, um, pin wall here, then you have a certain K value, etc. If you have a cantilever wall, there's a certain K value, etc. Right? So that table is right here. Effective length factor, K, Again, there's a table. You need to know if you are here or here or here. This value here is when the wall is restrained against rotation at one or both. Then you use that. Unrestrained against rotation. That means this is when you have a pin and a pin wall. The wall can rotate. So rotation we're talking about is that theta, there, right? Braced against lateral, not braced against lateral translation, 2L. Maybe the wall like that, not braced. This fellow can, if you apply, let's say wind load is hitting, the wall can sway like that. This is not braced against lateral rotation, so you can use a K value of 2 there, right? Now the value that you calculated above the PN has to be reduced by a factor, and we talked about that factor. The factor is like you need to find out which zone you fall. Are you in the that depends upon your strain in steel. If your strain in steel is in the tension control area, then you pick up your value from there. If the strain in steel in the compression controlled area, then you if the strain in steel is here, then you pick up your phi value from here. If the strain is in the transition area, then you pick up let's say your strain falls here, then you do interpolation between this point and point A and point B. Talked about that, and that is everywhere in this particular section there, right? Now in plane shear. By in plane shear, again we're talking about your wall there, wall like that, and the shear is in plane. So let's say someone is pushing it like that. So shear is in this plane, right? In this, the shear is happening along this plane, right? So in plane shear, how do you calculate your nominal shear strength when the shear is in plane? Correct. So eventually they'll give you a formula, the nominal shear strength. Obviously, this is a reinforced wall, so the strength will come from a component of concrete. How much will the concrete take? How much shear can the concrete take, and how much shear can the provided reinforcement take? So it is a like any other like a beam example. Your final strength, shear strength, it depends upon how much the concrete can offer and how much the steel can offer. But there are certain limits. Now when you, if it is a beam, you know what is your let's say this is the reinforcement. You know your effective depth there. You know your BW, so you know the area, shear area and all that. But when it comes to wall, um, the again, this is the height of the wall, this is the LW or width of the wall, and here this is the terminology which we should remember. So H is the thickness of the wall. Now for in-plane shear design, H is the thickness of the wall. D, which you will need in formula like that, that D has to be 0.8 times of LW. So LW, 80% of this LW is the D, right? And you know H. The reason we're talking about this particular D here is because to calculate the strength, to calculate the VC value, you need to use this formula here, and it uses H and it uses D. H is the thickness of the wall, D is 80% of the LW. LW again is this dimension here. LW, this is the height, HW, whereas that dimension here is just H, right? And there are certain, in shear we always see this pattern or trend that there is an upper limit for everything. So your Vn shall not exceed this particular value here, correct? And how do you get the Vn? Vn you calculate it based on this and that. Now how do you get this one? That one comes from this is the capacity, how much can, this is the shear that the concrete can take. Unless more detailed calculation is made, that value should not exceed this number here, right? And then we'll talk about how VC can be calculated, correct? So in this page, the only important detail, I mean, one of the important detail is that wherein this is the um, upper limit on the Vn value, correct? Now it says it is permitted to calculate the VC in accordance with, they gave you a nice table and you can pull your VC value. Obviously VC, this is a section being subjected to a positive, I mean an axial force, right? It's not plane shear, but there is an axial force. So there is an NU that is affecting the shear capacity. Um, so if you go to this table here, again you need to know when it is a table, you need to, this is for non-pre stage, you have to start from top, and you also have to pay any attention to the footnotes. There is a simplified option of calculating your VC, and there is a detailed option. So you need to understand if you fall here or if you fall here, correct? And then you need to understand if the axial force that is on the wall, so that is your wall, if the axial force, is it pushing down and causing compression in the wall, or it is some sort of tension in the, or is it a force that is causing some sort of tension in the wall, right? This is something slightly rare, but then obviously code is talking about that. So if you have your wall being subjected to compression and you are interested in to calculate the value of VC, again, why do we calculate VC? So that VC can be added to VS to find out your nominal capacity, shear capacity, in plane shear capacity of your wall, right? So to find the nominal strength, you need to calculate VC, shear by concrete, shear by steel, right? When you apply shear, in plane shear, it is not just the concrete that is resisting. Maybe there is some reinforcement, longitudinal reinforcement. Sorry, maybe there is some transverse reinforcement, and that can also take some amount of shear. And your concrete, depending upon how strong it is, it's going to take some amount of shear. That will dictate, the sum will dictate your nominal strength, right? If it is tension, you use that value. The only thing is you need to pay attention to this NU. It will be negative when your wall is under tension, right? And there's a detailed procedure for a breadth exam. I don't think they'll get into that level of detail because it needs a decent amount of computation, right? So that's about VC. And this is about VS. VS has to do with the area of the shear reinforcement, that is that, and the strength of the, obviously that depends upon the strength of the shear reinforcement steel. Sometimes you have a 60 ksi longitudinal steel, but then the shear reinforcement may be only 40 ksi. So you'll have to pay attention to that. And D, we talked about D is 0.8 times of the length of the wall, and then S is the spacing of that shear reinforcement, right? Um, so for example, you have a wall like that, and subjected to shear. Uh, Longitudinal reinforcement is running like this. That's not what we are talking about. Shear reinforcement might be running like that, correct? Now we are talking about spacing of the shear reinforcement, right? Not spacing of the longitudinal reinforcement. So that is this fellow here. Alexa, stop. So that's about shear. Now we get into the next topic here, which is reinforcement limits, right? So let's say let's talk about out of plane shear. We talked about in plane shear. So out of plane shear is your wall is like that, right? And then there's some load pushing it like this, which is trying to shear that particular section of your wall out of plane. I mean, this is when they say plane, they're referring to uh, this area, this plane, okay, out of plane. So this is out of the plane, right? Um, so like any other, like a beam, for example, if your applied load VU demand or applied shear demand is less than half the capacity. So this is the capacity of concrete. PVC is the capacity of the concrete. less than half that, then you only have to provide minimum reinforcement, minimum transverse reinforcement. Obviously, shear is being taken by the transverse reinforcement. And the roti percentage of the transverse reinforcement by gross area, that particular percentage is in this particular table here. So it's in that table there, right? So if you go to the table here, again, you need to be careful. So this is where the demand is less than half the capacity. So then when that happens, you don't have to provide full shear reinforcement. You just have to you cannot get away without providing shear reinforcement. You have to provide a minimum percentage, and that percentage values are all here. But then before you get here, you need to understand if you fall there or if you fall there. This is cast in place, precast. Let's say your wall is cast in place. Let us say, and then you need to first column deformed bars. Yes, deformed bars. I'm using deformed bars as my transverse reinforcement. Let us say. Then you need to use. Um, then you need to use. Um, you need to find out if what the diameter of your bar is. Are you less than number 5 or greater than number 5? Let's say you're greater than number 5, or let's say you're less than number 5. Then how strong is your shear steel? Are you this or are you this? Based on that, you decide the percentage of longitudinal reinforcement and transverse reinforcement. Again, longitudinal reinforcement along the length of the wall, right? It is the wall. There is reinforcement running like that, and there is also reinforcement running like this. Correct. So this is that which is row transverse, and this is this fellow here, which is row longitudinal. Correct. And it is a percentage. So let's say if you choose a strip 12 inches wide and you know the thickness, then you can find out the area of steel divided by that area, and that should be this value there, right? So that's about this table. Now what happens if you are not if your shear is greater than half the shear capacity? Then A and B have to be satisfied. A is that, B is this fellow here. Then your percentage of longitudinal reinforcement shall be according to a rule, shall be calculated by this equation here. PL or rho L is calculated by that equation, and you come and then you compare that with this one. Um, the greatest of the values calculated by equation that and that particular number, but it should be less than, but it should not exceed the PT value, right? This is not PL, this is rho T value in accordance to the table there, right? So just a simple rule. I mean, you translate the English into arithmetics, and then it should be good, right? So that is about if VU is greater than phi times of VC, right? So in short, this table is going to help us choose the minimum percentage of the longitudinal and minimum percentage of the transverse reinforcement that needs to be included in the wall. Right? And then these are some basic things. Reinforcement detail, obviously cover depends upon the exposure and all other details. You go to this section, figure out the cover. The development length we talked about in a video at length. LD values, which are usually a function of your FC prime, your Fy, your lambda, um, the diameter of the bar, and a bunch of modifications, modification factors. There are a bunch of 1, 2, and 3 modification factors. So your development length depends on that, and you can find that here, right? So development length of the bars that are running in the wall. Splice length, again, we talked about it in a separate video. This is when you're trying to splice two bars, depending upon the contact splice or non-contact splice. You can calculate the length of splice needed, right? Now we talked about the minimum percentage, we talked about thickness of the wall, we talked about the percentage of longitudinal steel, we talked about the percentage of transverse reinforcement. Now, how spacing of the longitudinal, again, longitudinal reinforcement, spacing. So that means you have bar here, bar here, bar here. What is that? Uh, what is the spacing there? So that depends upon lesser value of this and that. So you compute 3h. H is again your thickness of the wall, not the height of the wall, and then 18 inches, and you conservatively pick the lower or least value, right? And that is for cast in place walls. If you have in plane strength spacing, cast in place walls, this particular criteria, in place strength spacing longitudinal reinforcement shall not exceed that particular criteria. The spacing is for longitudinal walls in precast walls. This is for cast in place. Again, the same trend: cast in place, precast. There are some rules. Rules have to do with finding one value, finding the other value, finding out the lesser of A and B. You know what H is. Again, H is the, if this is the wall, H is the thickness of the wall, not the height of the wall. Right. So you can find out those. So you figure out how to space the reinforcement. Right. Now again, same thing, transfer reinforcement. We talked about longitudinal, now we are talking about transverse. Again, transverse reinforcement is that reinforcement. So let's say this is the wall, this is the width of the wall, which is LW. We are talking about reinforcement like running like this, or the bad chicken scratch. Reinforcement running like that, correct? And we are talking about spacing, that spacing. That is the spacing of the transverse reinforcement. So S here is that S, right? That depends upon, again, you find out these values and simple rules, um, precast walls and cast in place walls, different rules for both of them. So you figure out that one, right? So for you, if you have longitudinal reinforcement, obviously you need some lateral support for the longitudinal reinforcement. If the longitudinal reinforcement is required for axial strength, then or if the AST value exceeds a portion of the AG, longitudinal reinforcement shall be laterally supported by transverse ties, right? So you have longitudinal reinforcement running like that. You somehow have to support it with the lateral tie. So that's about the wall's most important details. Yes, there are some other details here, but this is a little too much for a breadth type question, right? So, so the next section is diaphragm. So we covered walls at length in this section, right? So the main important thing is to correlate uh, the I mean the symbol with the sketch. You know what H means now. You know what, if you suddenly see LW, you know what LW is now, right? You suddenly see a row L, then you know what row L is. Suddenly see a row T, you know what row T is, correct? If you see VU and VC, then you know what that is. You know what is VS. We talked about that, right? And then one thing very important is this value here, the D. Many times we all know how to calculate the D value for a beam, that is from the outer compression fiber to the center of the reinforcement. Whereas for a wall, how do I calculate the D value? And that is a very important detail there, right? All right. Thank you very much. If you have any questions, let me know.